Okay, this video is about learning how to use the factor and the remainder theorem. This is in section 4.2 where we're learning some polynomial topics. And so, last video was synthetic division. That is what we're going to be using here. So you have a worksheet to go along. We're going to do the first half of the worksheet on this video. And so it's this, it says, part A says divide the following polynomials p of x by x minus c using synthetic division. So let's just run through this. It won't take long to divide these using synthetic division. So number one, c is 3. We're going to go through here and put the coefficients 2, negative 5, negative 3. Bring down the 2, multiply up 6, 1, 3, 0. Okay. Let's interpret remainder, x to the 0, x to the 1. That's what I know. All right, so this is equal to 2x plus 1. The remainder was 0. Okay. Number 2, let's do this. This is of the form x minus c. In this case, c would equal to negative 2. Negative 2. Draw your big long L. We're going to have 1, negative 3, negative 14, negative 8. Bring down your first guy, 1. 1 times negative 2 is negative 2. Add negative 5, multiply positive 10. Add negative 4, multiply positive 8, add 0. Interpret 0, x to the 0, x to the 1, x to the 2. This tells me that this polynomial divided by that polynomial is equal to 1x squared minus 5x minus 4, and the remainder was 0. Okay, number 3, synthetic division, c is negative 1, big long L. Coefficients 1, 5. I'm missing a term, put in your placeholder 0, and 7. Bring down 1. 1 times negative 1, negative 1. 5 minus 1 is 4. 4 times negative 1, negative 4. 0 plus negative 4, negative 4. Negative 4 times 1, 4. 7 plus 4, 11. Interpret. Remainder, x to the 0, x to the 1, x squared. That means that this polynomial divided by that polynomial is equal to 1x squared plus 4x minus 4 plus 11, the remainder over what I'm dividing by, x plus 1. Okay, great. Down here, let's use synthetic division here. C is equal to 4, long L. My coefficients are 1. I do not have an x squared term. Put the placeholder in, 0. Negative 13, negative 12. Goes like this. Bring down the 1. 1 times 4 is 4. 0 plus 4 is 4. 4 times 4 is 16. Negative 13 plus 16 is 3. 3 times 4 is 12. Negative 12 plus 12 is 0. This is my remainder, x to the 0, x to the 1, x squared. That means that this polynomial divided by that polynomial is equal to 1x squared plus 4x plus 3, and the remainder was 0. Okay, that was part A. It said simply to divide using synthetic division. So we did that. All right. Part B says use the remainder theorem to evaluate P of C for these 4 examples. All right, what is the remainder theorem? I wrote it up here so we know what it is. The remainder theorem says if a polynomial P of x is being divided by something of the form x minus c, that's what we had going on in all of these examples. So we have a polynomial dividing by x minus c. Then the remainder, whatever the remainder is equal to that polynomial evaluated at that value, c. So let's go through and interpret this, the remainder theorem, for all of these. Number 1, this meets the condition, polynomial divided by something of the form x minus c. Then we can say P of c, so let me do one thing. Let me call all of these P of x, and down here this is x minus c. Right here, this is our P of x, and this is our x minus c. This is our P of x, and this is our x minus c. This is our P of x, and and this is our x minus c. So that'll help us see what's going on there. Okay, so if this is our polynomial and this is our x minus c, by the remainder theorem, I can say that if I evaluate this polynomial p at the value c, which is 3, p of 3, it equals to whatever the remainder is. So in this case, the remainder was 0. By the remainder theorem, I can evaluate that polynomial at that value. Right here, let's apply the remainder theorem. P of negative 2 equals to the remainder, which is 0. Number 3, P of, what was our value of c? Negative 1. Negative 1 is equal to what we got for the remainder. In this case, it was 11. P of 4 is equal to whatever we got for the remainder, which is 0. That is the remainder theorem. That's how you apply it. Okay, that's part B. Part C says, use the factor theorem to rewrite P of C with x minus c as a factor. So let's see. Use the factor theorem to rewrite P of x with x minus c as a factor. So let's look at what the factor theorem says. It says if you have a polynomial p of x, a polynomial p of x has a factor of x minus c if and only if p of c equals to 0. If you take that value and you plug it in and you get 0, then it's a factor. Let me tell you what some other words we call. If p of c equals to 0, you know what c is? This is called a solution. This is called a root. This is called an x-intercept. This is called a 0. That is what we give the name for something like that, which we've heard several times, and here it is again in sort of a new light. So, all right, some of these polynomials fit this factor theorem category, and one does not. Which of these things doesn't belong here if you ever saw that little segment on Sesame Street? Let's see. P of c equals to 0. Here, okay. Number 2, here, okay. Number 3, p of negative 1 equals to 11. No, this one we cannot apply. So for this we cannot apply the factor theorem. I'm not going to worry about 3. For p of 4 is 0, we can apply the factor theorem. So what our job is to do is to rewrite p of x, which is this, 2x squared minus 5x minus 3 into factored form, since we know that p of 3 equals to 0. All right. P of 3 equals to 0. How can we rewrite this? Well, let's just look at this. Since there was no remainder, this is how we can begin to write this. I'm going to erase the division so we have more space, and I think it'll be clear. We already said that p of 3 was 0, right? P of 3 was 0. P of 3 is 0. So what does the factor theorem says? It says that x minus c, so p of x, has at least one factor of x minus c, or x minus 3. Oh, well what else can it factor into? Whatever we got when we did that division. 2x plus 1. You can kind of see that. If I took this polynomial and multiplied both sides by the denominator, x minus c, that's what I get. This is how I can write it in factored form. Let's try number 2. I'll erase the division so we have more room right here. Okay. Ready? We said, oh, can we even apply the factor theorem? Does it apply? Yes, it does. So it's saying this much of the factor theorem says p of x has at least one factor called x minus c. X minus negative 2 is really x plus 2. That's one of the factors. What's left? Oh, this, after we did that division, this is the other part. That's what it can be divided into. What if they went further, and this is where we're headed with this, and they said, find all of the zeros. See, we found this one, x is negative 2. How would we find these? Well, we would set this quadratic equal to 0 and solve. We would either solve it by factoring or completing the square or quadratic formula, but we could find the rest of the story if we needed to. And later on, we will need to. 3 we could not apply the factor theorem because it did not fit the right, did not have the right conditions for us to use it. But we can use it on 4. So again, let me just erase where we divided so we have more. more room. All right, so we found out that P of 4 equals to 0. All right, then that means there's a factor x minus c. So P of x, in this case, can be rewritten into x minus 4. Okay, x minus 4 times what else? Times whatever we got there. If that's hard to see, look at this. What if you simply multiply both sides of this by x minus 4? This is what P of x equals to. P of x is equal to x minus 4 times x squared plus 4x plus 3. And what if I said, oh, let's just take it a step further and let's find all the zeros now. We could totally do that because this is quadratic. Set that equal to 0 and solve. Either it will factor or quadratic formula or completing the square. We can do it. All right, great.